Hi, everybody. My name is Maddie Murphy. I'm a PhD student at University of St. Andrews, and I'm going to be presenting the findings of my master's dissertation from 2019. So hopefully I can convince you why the silicon isotope system is useful in providing some new insights into the formation of the earliest continental crust. And in this study, we measured silicon isotopes in some of the oldest extant rocks on Earth, the tonalite-trondhjemite-granodiorite, or TTGs, from the Itzak gneiss complex in southern West Greenland. So silicon isotope geochemistry is somewhat of a niche field, so I just wanted to give a background on this area of research. And there's a couple of main takeaways that make this system useful in studying the primary processes that form the oldest crust. So the first major takeaway is that we can precisely measure silicon isotopes in Phanerozoic igneous material, and these deviations reflect predictable but small changes that are namely a result of increasing silica content as magmatic differentiation proceeds. So here I've just included the value for the bulk silicate earth for silicon isotopes and this small range of predictable values for modern basalts and modern granites. Later on, I'm going to get into better detail about this predictable variation between silica content and the isotopes. But for now, the important thing to know is that these high temperature igneous rocks have small variations in the isotopes. The second major takeaway of this system is that silicon isotopes are resistant to metamorphism. And we know this about the system because of data from granulite facies or fascies, xenoliths from the Chudley and McBride xenolith suites from Queensland, Australia, which exhibit these small deviations in silicon isotopes and reflect signatures that are pretty much indistinguishable from their inferred protolith material, and again hover around this value for the bulk silicate earth. So this suggests that even up to a very high grade, silicon isotopes are resistant to metamorphism. Additionally, the system is resistant to hydration, which comes from evidence of serpentinized abyssal peridotites, which have silicon isotope signatures which are distinguishable again from unserpentinized lithologies, suggesting that, and again, these all hover around this bulk silicate earth value, and this suggests that the system is resistant to hydration. So the last thing to note about this system is that whereas high temperature processes have kind of a small sub per mil impact on silicon isotopes, surface processes will fractionate the isotopes to much larger values. Specifically, two processes have large opposite effects on the isotope system. Clay formation during weathering will drive silicon isotopes to very negative values, whereas incorporation of authigenic or seawater-derived silica will drive the values to very positive ones. So this is all of interest to us because when we look at igneous material, the incorporation of non-igneous inputs to melts will still record the silicon isotope signature of these processes. So for example, S-type granites have lighter silicon isotope signatures than I or A types, reflecting this incorporation of clay-rich sediments in their melt source. So given all these knowns about modern igneous material, we wanted to measure silicon isotopes in some of the oldest rocks on Earth to find out if their signatures could reveal something interesting about what was melting to form the earliest continental crust. So just as a background on these samples, they were collected by Steve Morbath in Southwest Greenland and given to my supervisor, Paul, before my dissertation started. And they come from the Itzak gneiss complex and the Ishua supercrustal belt. And we did actually measure silicon isotopes in various different lithologies, but the TTGs are kind of the star of this study, so I'm just going to focus on their silicon isotope signatures. And depending on the silicon isotope values in TTGs, we might be able to track their inferred source material. So given that there's these samples have been analyzed by a number of different workers for different geochemical parameters, there are many different interpretations about how the Eoarchean crust in Greenland formed. And while this, this idea of TTG genesis is highly debated, there seems to be consensus that TTGs formed from partial melting of a hydrated basaltic protolith. And we can test this with silicon isotopes, given these precedents about non-igneous inputs to melts in the modern igneous material. So now that we all are kind of on board with silicon isotope geochemistry, if the melts reflect contamination with sediments, the TTG signatures should kind of reflect an S-type granite signature, whereas if they are derived from melting of a serpentinized basalt, they would result in TTG signatures that are closer to an I or A-type granite. So given this, here are our results. So here I've included the results for our Greenland metabasalts and our TTGs. And I've included our metabasalt data to show that even though we only had 2 samples, and this is an area of future research to constrain a definitive silicon isotope composition for these, our 1 sample falls directly within the value for the bulk silicate earth, and the other is slightly lighter than this value. Our TTGs define quite a limited range. We had 10 samples, and they reflect these small deviations in silicon isotopes, but this is an interesting finding because overall they are heavier than what we would expect. So in comparison to Phanerozoic granites, as well as this contemporaneous metabasalt samples, our TTGs are isotopically heavy. And this is kind of a curious finding because if we take our metabasalts to represent this inferred precursor TTG material, there must have been something else melting with them to generate this heavy TTG signature beyond just that of a hydrated basalt. So in order to better explore this, I've plotted our TTG data for their silicon isotopes against their silica content. And this line represents this predictable trend in Phanerozoic igneous material between silicon isotopes and silica content, known as the igneous array. And I've plotted our TTG data here to show that on average, they deviate from this array and in a heavy direction. And so as we learned before, if they reflected straightforward melting of a hydrated basalt, they should fall along this array. So the fact that they're overall heavy is our interest here. So I've just included this trend line to show that the TTGs still exhibit this predictable relationship that's observed in Phanerozoic igneous material, but there's this 0.10 per mil offset from the igneous array line for modern material. And this offset for the TTGs represents the influence of a heavy contaminant in their formation. Going back to this idea of melt contaminants, if we plot modern S-type granites along the igneous array, their signatures will fall below the array than what we would expect for their silica content. And this reflects the incorporation of these clay-rich sediments into their melt source. So our TTG data are antithetical to this. And I would argue the best explanation for this is incorporation of seawater derived or silicified, seawater silicified material in their melt source. And this aligns with the idea that the silicon isotope composition of the ocean is, or the fact that the silicon isotope composition of the ocean is +1 per mil, and it's inferred to have been around the same signature in the Archaean, as well as the fact that the Archaean oceans were silica saturated in the absence of diatoms and other silica secreting organisms. And so the fact that Archaean cherts were widespread might support this heavy TTG signature because this inferred basaltic protolith may have been intercalated with cherts to melt to form TTGs. And this is interesting because it's not unique to the TTGs of Southwest Greenland. So there were 2 other studies that came out when my dissertation was being marked, actually, that found these heavy silicon isotope signatures in granitoids from the Paleo-Archean through the Paleozoic, suggesting that so far heavy silicon isotopes are common in Archaean TTGs. So the surprising finding from these silicon isotope studies of the rocks of Archaean Greenland are that there's some systematic source driving their silicon isotope signatures to be heavier than what we would expect and reflect melting of something beyond just a hydrated basalt. And crucially, this is seawater derived. So this narrative is starting to come together that there was sufficient, well, the interesting part, I guess, about these positive silicon isotope signatures in the ocean is that in order to generate these values, there would have to be sufficient weathering to get heavy silicon isotopic fluids into the ocean. And so this would necessitate that the weathering products or the sediments had complementary negative values. And what's really cool about this is that we also measured the Eoarchean metasediments from the Ischua Belt, and our metasediment data support this. They are quite negative in terms of their silicon isotope values. So this supports this theory of a holistic Eoarchean silicon cycle involving an early hydrosphere in which early continental material was being weathered, and then this isotopically heavy runoff was going into the ocean in which cherts were precipitating, and then were intercalated with this meta basalt that was serpentinized, which melted to form TTGs. And that is the proposed explanation of these heavy TTG signatures. Whether these signatures are ubiquitous for Archaean TTGs is still up for debate. And they don't necessarily clarify the geodynamic setting in which TTGs were formed, because these signatures could be explained in a subduction or a vertical plateau setting. And so one of the future directions of silicon isotope geochemistry research is to understand better how these major geodynamic and climatic events would affect this system. But I believe the interesting finding from this study is that silicon isotopes potentially reveal a unique aspect of TTG formation involving a primeval hydrosphere. And so hopefully this system will further be used as a way to study the primary processes involved in forming the crust. So thank you for your time.
Super, thank you, Maddie. That was really fascinating. And yeah, great to see a new tool being used on these old rocks and that it's robust in the face of high temperature metamorphism. So a bit of a discussion in the chat. Can you clarify, so some TTGs, you sort of classify them as high, medium, or low pressure based on their trace element signatures, but in terms of the TTGs you were discussing, do they belong to any of those categories? Are there any systematics with respect to your data?
I believe these are medium and high pressure TTGs, if I'm correct. There's, I'm just reading the questions here. I think that's one area that, because in the dissertation we talked about how specifically the pressure might impact like the melting involving some type of contaminant, and that's definitely something that was beyond the scope of the study. But yeah, that would be interesting to note whether the pressure, how that would impact this inferred contaminant.
Cool. Yeah, definitely a future direction there. So Simon Harley's asked, are you measuring the silicon isotopes in the whole rock, in plagioclase, or in zircon?
Yeah, so these are bulk rock powders.